Hello, we're going to solve a buffer problem. And this one is to design, which means you would go in the lab and weigh something out to get a buffer system that works at pH 10.94. And let's say you have three options where you can go into the stock room and measure out some weak acids and bases, and you can see our options here, 1, 2, 3. And then we can quickly assess which one to choose by looking at the pKa, the negative log of the Ka expression. And we can see quickly here that 10.32 is quite close, at least compared to the other two, of the desired pH. So our problem is here today, what can we weigh out, and in fact, how much can we weigh out in grams of the potassium salt of the weak acid, which would be potassium hydrogen carbonate. This would give us a neutral ionic compound because the positive one would balance out the negative one, hydrogen carbonate. How many grams would we need to combine with the potassium salt of the weak base? And we're trying to produce a buffer, 1 liter of it, and 1 molar, and this is related to the buffering capacity here. We can use the Henderson-Hasselbalch equation to determine the masses of both of the weak acid and base, because we can get the concentrations of the weak base and the weak acid. Well, the problem already states we need 1 molar of this weak base, and we need 1 liter of it. When we multiply those together, we get 1 mole of the weak base. And so we need the whole salt here in order to get the right mass to weigh out, because you'd be weighing the potassium ion as long as with the carbonate. You look up the molar mass of this, we can see that that is 138.2 grams per mole, and I've set that up backwards. We can easily erase that. We want our moles to cancel out, so it's 138.1 grams per mole, and that gives us 138 to 3 decimal or 3 significant figures grams of the weak base that we need to weigh out. Alright, so we've gotten half the problem done. Now we just need to figure out how much of the weak acid we need to weigh out. Well, the problem states we need pH of 10.94, our pKa is 10.32, and we have the log of 1 molar, because we enter the concentration here, divided by x. We just need to solve for x, and it'll give us the concentration. So we subtract 10.32 from both sides, and that gives us 0.62 equals the log of 1 over x. Well, to undo the log function, we need to raise both sides. We use the 10 to the x function, and so 10 to the 0.62. Plug that into your calculator, it gives you 4.69. And 10 to the log function, then these undo each other, and you're left with 1 over x. So you can flip both sides around, or I like to think of it as multiply both sides by x, divide both sides by 4.69, and you can see the concentration is 0.240 molar, or moles per liter, of the weak acid, potassium hydrogen carbonate. Well, we know we want 1 liter of this, so that'll cancel that out, and we'll be left with moles, and if we multiply by the molar mass of potassium hydrogen carbonate, what I had to go look up, and you can see that essentially multiplying by 100, and that gives us 24.0 grams of potassium hydrogen carbonate. All you need to do is go weigh out that on your balance, go find potassium carbonate, add those together in 1 liter of buffer, and that solves our problem.